Hello, so welcome to another video on how to solve ODEs in MATLAB. Today we want to solve another problem, basically simple problems uh, involving a plug flow reactor. So we can see that the problems are simple, but once you get the concept of the implementation, you can apply it to more complicated problems. So you have to start from simple problems, and if you understand the structure, you can then apply it to more complicated ones. Now we have a second order differential equation with some boundary conditions. So you have the boundary condition at x equals 0 and the boundary condition at x equals L. And you have some of the parameters given here. So we want to look at how we can implement these in MATLAB. Okay, so let's jump to MATLAB and to solve this. Okay, so first you define the parameters that we have. So the differential coefficient U, K, L, and C in, and then you write the equation, the ODE. So again, you write it as an anonymous function. So where you have, the function takes X and Y. So this Y is a matrix of all some vectors that you have in the problem, and X is because it's you're doing it with respect to X in space. So that's why you have X there. Now you need to, return the first derivative and the second derivative of Y. So again, you have to first decompose the second order problem to first order. Now, what you have, the equation that we have is d squared c dx squared minus u dc dx minus kc equals 0. So you need to first write the equation having only the squared c dx squared on the left-hand side. So if I rewrite this problem, I'm going to have d squared c dx squared equals u over d dc dx minus k over dc equals 0. So again, you cannot solve this directly. You have to decompose these into first order. Now, C, you have to set C, Y1 to be C. Okay. So if C is Y1, it means that the first derivative, dx, dc dx, can be Y2. Okay. So dc dx is Y2, and then C is Y1. Then I can rewrite this equation by substituting C here and dc dx there. So which means the right-hand side of that equation would therefore be u over d y2 minus k over d y1. Okay, sorry. This will be plus here. Yeah, that should be plus there. Okay, so it should be y1 like that. Okay. And so that's what you're going to write. Again, the ODE, the function will return the first order, which is y2, the first order derivative, y2, that's why it is y2, and then the second order, which is equal to that. So the second order derivative is equal to that, which is now equal to that. So which is u over d y2, and then k over d y1. So remember, y is a vector. So take note of that. Y is a vector of c and the c dx. So that y is that vector. Okay, so that's why c is y1 and the c dx is y2. So this is y1 and then this is y2. Now, the boundary condition, similarly, you do the same thing. So the YA, again, A is at the inlet, B is at the exit. So you specify the boundary conditions at those those two extremes. So the boundary condition that you have is UC in equals UC at x equals 0 minus D dc dx at x equals 0. So this is at the inlet, and then at the exit, DC the x at x equals L is 0. Okay, so and that's what you have there. So boundary conditions are written such that everything is equal to 0 before you can specify it. So I need to move this to this side. So it's going to be, if I write this, it's going to be UC in minus everything UC minus DC dx. And you know that similar to what we did before, YA, YB, the first derivative, will be Y2, then C will be YA for the boundary condition. So that's why this C is written as YA1. This is at the inlet. So it is YA, this A is what represents the inlet. 1 is because it's the first row in that vector. So remember, it's C and D, C, D, X. So, and then this one is going to be YA2, which is what we have there, YA2. And then the boundary condition, the second boundary condition at the exit is basically DC dx equal to 0. So all we need to do is just specify DC dx, which is YB2. So B, because it's at the other end. This is the inlet, and this is the exit. Okay, so that's how you specify the boundary condition. Then the initial guess, again, you specify the initial guess by using BV init. So linspace 0 to 0, comma L, comma 20 is saying, okay, generate from 0 to L 20 grid points. So the 20 points, and then specify the concentration and 0. Specify the value of the of y at those points. So y, remember, y is C and D C dx. So what we're saying is that, okay, at the inlet, so is equal to C in, and the derivative is equal to 0. That's what we've done here. Okay. And then we solve it by calling the solver BVP for C. This is one of the solvers that you can use. Specify the function, the boundary condition, and the initial condition. So when you solve it, so note that for boundary value problems, you'd first need to solve the problem and make sure that it converges first before you can then evaluate that solution at the specific point that you want. Unlike initial value problem, where you can specify the time point that you want to run. But for boundary value problem, you first solve it, and then you extract the solution at those specific point that you want. And that's what we're trying to do here. So before you plot, we'll first specify the points that we want to extract the data points. The more data point you have, the smoother the curve. So now we want 100 points, so between 0 and L, so the inlet and the exit. And then we use this function, deval, to evaluate the solution at those points that we've just created. Okay, so once you do that, then you will now have this C will now contain 100 points. So 100 points, so which correspond to the X values and C. So you have the 100 point, and then you have C that matches each point. And then you plot it. So that's what we're doing there. All columns, first row for C. So let's run it. When you run, what do we get? We run that, yeah, and you get the solution. So concentration from the beginning at 2. At the exit, you have about 25, and at the inlet, you have about 62.5. Okay, so that's it for this video, and I will see you in the next. I hope this helps. Bye-bye.